So as a review from the previous video that we had, there are several different types of chemical reactions. So we have combination synthesis reactions where we're essentially creating a new compound from simpler substances. Decomposition is essentially the opposite, where we are breaking something down. So like a larger molecule breaking down into simpler substances. We're going to talk about single and double replacement in this video, as well as discussing neutralization, oxidation, and combustion reactions. So just to review, combination, it's a reaction in which simpler substances are combined into more complex ones. So a simple example would be like A plus B makes AB, and we talked about specific examples in the previous video where we can call them synthesis reactions. So a metal with oxygen, so some metal combining with oxygen, making the metal oxide, whatever that formula is, depends on the metal. Reaction of a nonmetal with oxygen. So I think one example we had was like sulfur with oxygen, making sulfur dioxide, and then reaction of a metal with a nonmetal. So just some metal with some nonmetal, and then the formula depends on the charges of the two ions that we form. So that could depend, but we talked about those in the previous video. And then next thing that we already talked about, but just to review, is decomposition. So a single compound is broken down into two or more simpler substances. So the example would be some compound AB breaks up into A plus B. Now, heat is usually required to start these types of reactions. Ionic compounds containing oxygen will often produce oxygen gas, and this is an example we have. So we have this mercury oxide, mercury 2 oxide, and it's breaking down into liquid mercury and then oxygen gas. Now, before we go into single displacement or single replacement reactions, we're going to talk briefly about what we mean by activity series. So when a metal undergoes a single replacement reaction, it displaces or replaces another metal from a compound or an aqueous solution. So the metal that displaces the other metal does so because we say it's more active or more reactive, if you will. The activity of a metal is the measure of its ability to compete in a replacement reaction. And in an activity series, we're basically ordering the metals, so we're creating a sequence of metals, and they're arranged according to their ability to do this, ability to undergo a chemical reaction. Now, this is a relative activity series. We could put more elements in here. You could look up activity series and you could get a much more comprehensive list. But for the most part, these are ordered from most active to least active. And one thing I want you to notice, some of the metals that are here on the least active end, we have like copper, silver, and gold, for example. Those are usually used in coins, in money, because they are so unreactive. So we make jewelry out of silver and gold because it doesn't react with oxygen or other chemicals in the air. Meanwhile, the elements that are on this end, so we have lithium, potassium, calcium, sodium, strontium and barium. So all of these for the most part, the most active metals are group 1, group 2 metals, so the alkaline earth metals. They are extremely reactive, meaning if you had a chunk of solid neutral sodium, so not ions, but atoms, it would be extremely reactive when exposed to water, for example. But this is just generally what we mean by activity series. So we have most active, so the elements or the metals are most willing to give up those electrons to become ions. And on the other side, you have elements that are perfectly happy being neutral, and as a result, they can be very useful in industry. So the most reactive ones appear first in the list, and the least reactive ones appear last. Now, this activity series comes up when we talk about single replacement reactions. So it's a reaction in which a more active metal displaces or replaces another less active metal. So in this example, we've got iron and copper, and then the reaction that we're proposing, notice that the iron and the copper have essentially switched places. So the iron started off in the solid state, and then in the product side, the copper is in the solid state. So that's why it's called a single replacement reaction, because essentially this iron has come in and just bumped out the copper, and then the copper came out. So we have just one position changing, if you will, to contrast that with double replacement, which you'll see it's kind of like two things swap places. But going back to the activity series, if a metal precedes another in the activity series, it will undergo the reaction. So these are the two metals. We have iron and copper, and we're talking about iron displacing the copper. So it's kind of like copper is bound to the sulfate. The copper is being bumped out. It's being displaced by the iron. And if we go back and look at our activity series, here's iron and here's copper. The iron did appear before the copper, meaning that we should see a reaction. So if a metal, the iron, precedes another in the series, which it did, it will undergo the reaction. So that's kind of what they mean. You can take any example. If the solid metal precedes or appears before, if it's earlier in the list compared to the one that's already in the compound, then you will get a reaction. If the solid metal appears after the other one in the list, then we would put NR for no reaction. So you'd have, A plus BC, and we're saying that if this solid metal A was after the element B in the list, then we would say NR for no reaction to say that nothing's going to happen. Now, one important thing about hydrogen, metals that appear before the hydrogen in the list will react with acids, and those that follow hydrogen will not react with acids. So the special thing about acids is most acids like hydrochloric acid, hydrobromic acid, or sulfuric acid, notice that all of these have hydrogen in it. So that's why we're pointing specifically to hydrogen to figure out if a metal will or will not react with an acid. More active metals react with acid to produce hydrogen gas and ionic compounds. So here's our iron again, and here's hydrogen. And if we go back and look at the activity series list, here was iron, and then here's your hydrogen. So it's before hydrogen on the list. Since iron is before hydrogen, we should see a reaction, and they're saying what we get is hydrogen gas and this ionic compound, where again the iron has kind of come in and displaced the hydrogen, and the hydrogen bumps out of the compound to become whatever it would be in its neutral state, which in this case, it's a diatomic gas. Metals less active show no reaction. So here's gold. And remember, we noticed that gold was at the end of the list with those coinage metals like silver and copper. We're going to see no reaction because gold appears after hydrogen in that list. Active metals in water, so a specific example that you should know about, it's essentially the alkaline earth metals. They are so reactive, they will react directly with water. So a few metals are active enough to react directly with water. We're calling these active metals. But it's essentially just those first two columns of the periodic table. And how reactive kind of depends. Some of them are explosive with water. Some of them it's just a furious reaction, but it's not quite explosive. One reason why it is explosive is you have the metal reacting with the water, and what we end up getting is a lot of heat and the hydrogen gas. And if you guys are familiar at all with the Hindenburg, you'll know that hydrogen is explosive. So if you have a lot of heat produced from the reaction because it's extremely exothermic, and you also have a bunch of hydrogen gas appearing in the reaction, that can trigger an explosion. It's a fun demonstration to watch, and I encourage you to look up a YouTube video, or perhaps I'll link to one. So another type of reactions that we're going to get into later in the course, but we're not going to spend too much time today, oxidation-reduction reactions. So these are reactions involving the transfer of electrons from one substance to another. And this can happen with metals, with non-metals. Quite often we will see it with metals, but like here we have a metal and a non-metal. And remember, this is sodium, the way they've written it, this is sodium neutral. So this is the neutral atom. And then this is diatomic chlorine. This is also neutral. But here in this compound, now the sodium is essentially a sodium ion, and the chlorine is a chlorine ion or chloride ion. So in order for this chlorine to become negative, it had to gain electrons. Where did those electrons come from? They came from the sodium. So an exchange of electrons must have occurred there. So we would call this reaction a redox reaction or an oxidation-reduction reaction. Redox stands for oxidation reduction, so we'll just colloquially just kind of say redox, and what we mean is oxidation reduction. Keep in mind this also clearly looks like a synthesis reaction because we have A plus B makes AB. So it's possible for reactions to have multiple classifications. You could definitely label this one as synthesis and as redox. So a lot of the reactions we have seen, we can classify them as oxidation reduction. How we determine if it's oxidation reduction or if it is an oxidation reduction reaction, we will get into in another video, but just know that when you are trying to classify reactions, it is okay to give them more than one classification. And then just like with this example, anytime you have a metal and a nonmetal reacting, especially when they're neutral, so this was solid sodium that was neutral and this was your chlorine gas, anytime you have a metal and a nonmetal reacting, you're probably having electrons being transferred from one element to another, which means we can classify it as oxidation reduction. Here's another example of oxidation reduction, a very common example. So basically the rusting of iron. Anytime you have just neutral iron, it can react with oxygen in the air to produce an iron oxide, which is composed of these ions. So iron metal, when we say iron metal, we're implying that it's neutral. So it's neutral atoms where we have the same number of electrons to the number of protons in the iron nucleus, but then it turns into ions. So iron 3+ means that it must have lost 3 electrons. Where did those electrons go? It must have gone into the oxygen atoms. Now, one thing that you guys should notice is this iron lost 3, this oxygen gained 2. Well, that gets into balancing, so how we account for exactly how many electrons are gained and lost. We'll get into that when we talk more in depth about oxidation reduction, because then those reactions are balanced in a special way, and we will go over that in much more detail. Just a couple terms though. So anytime a compound loses electrons, we say it's being oxidized, and anytime a substance is gaining electrons, we say it's being reduced. And this term oxidized, it's because oxygen quite frequently is the element stealing those electrons. So in this case, we have oxygen stealing electrons from the iron to create the iron oxide. So just in nature, learning about chemistry over the decades and, we've noticed that oxygen is typically the thief. Oxygen is often the one stealing, but it doesn't have to be oxygen. Oxygen does not have to be in a reaction in order for it to be classified as a redox reaction. It's just oxygen is commonly the element stealing those electrons, at least from what we've observed as we've been learning about nature. So that's where the term oxidized came from. And then just reduced, I don't really have a story for why it's called reduced, but reduced is gaining electrons. Oxidized is losing electrons. So make sure you maybe make some flashcards for those terms because they're very easy to get confused when you're first learning. So the next type of reaction is double displacement, but before we talk about that, we're going to talk about the solubility rules. So you could Google solubility rules and you might find a few more than what's on this list. But this is table 7.2, and I'm going to say that the most important ones that you should learn are these first 3. So essentially alkali metal ions, so the first column of the periodic table, and then the ammonium ion. So anytime you see these in an ionic compound, that means that the compound will dissolve in water, or we say it is soluble in water, or you'll use the physical state aqueous to say that it dissolves in water. So compounds like sodium chloride or lithium fluoride, we have first column metals, so those alkali metals, group 1 metals, those are in these ionic compounds, therefore these are soluble, or we will use AQ for aqueous when we write them in a chemical reaction. Anytime you see the acetate ion, it's generally soluble, and then also the nitrate polyatomic ion. Anytime you see those in an ionic compound, the compound is soluble. So then insoluble means that it's not going to dissolve in water. So if you had this compound, so something like with this rule here, carbonate, let's say you had barium carbonate as an example, because we have carbonate in the compound and it doesn't also satisfy one of these rule 1 exceptions. So these up here, we would say it's insoluble, and then we would use the solid physical state when it appears in a reaction. So that's what we mean by soluble and insoluble. Soluble means it's aqueous. Insoluble means it's essentially in the solid state when it's in a chemical reaction. And these solubility rules we are going to be using when we talk about double displacement reactions. So double displacement or double replacement reactions are when we have two ionic compounds in aqueous solution and the anions essentially switch places. So we have AX and BZ, and you see that the A and the B, or in this case they did it the Z and the X, they essentially switch places, so they switch partners, if you will. And then the products here, if either of those are an insoluble compound according to the solubility rules we just saw on the previous slide, then a solid precipitate will appear, and we would say that there is a chemical reaction. So a precipitate basically means we're making a solid. And we use the word precipitate, the way I think of it is precipitation means rain falling from the sky. If you have a test tube full of liquid in there, a precipitate would be a solid is forming and it's falling to the bottom of the test tube. So that was the connection that I made when I first learned this word. A precipitate is essentially a solid. You're making a solid compound and it'll fall to the bottom of the test tube. You could then use something like a centrifuge, or you could decant or pour off the liquid to separate the solid from the liquid. But anyway, if no precipitate is formed, so essentially if these two compounds here, if the two products are both soluble by the solubility rules we saw on the previous slide, then we would say that there is no reaction. So it might be, AX plus BZ, and we would write NR for no reaction. So a couple examples of double replacement reactions. So we have aqueous barium chloride reacting with aqueous potassium chromate, and we make these two compounds, barium chromate and potassium chloride. So from the solubility rules, barium chromate is insoluble, so we could go back and look at the rules and see which rule applies. We see that rule number 7 here, we talks about the chromate ion, and it says that that's going to be insoluble unless we're looking at one of the rule 1 exceptions, which are kind of like more important. So these first 3 rules are also the more important ones. Since we're not seeing that, barium is not doesn't appear in this list up here, and chromate is one that makes insoluble substances. That means the barium chromate is insoluble, so that means we get the solid physical state right here, and so we would indeed have a double replacement reaction. So here's a second example. Aqueous sodium chloride reacts with aqueous lithium nitrate, and we would theoretically make sodium nitrate and lithium chloride. However, according to rule 1, ions with sodium would be soluble, and rule number 3, ions with nitrate is soluble, so that's why we have aqueous right here. And then similarly, rule number 1 again, lithium is a group 1 metal, that's going to make it a soluble compound, so again we have aqueous. So since both of our products are soluble, since they're both aqueous dissolving in water, we say that there is no reaction. So it's okay to write out the products, but then you also indicate that there's no reaction. So this is what we would theoretically make for our products, but we understand that they're both soluble, so there's essentially no reaction. So the second type of reaction that is technically a double displacement is neutralization. So it's reaction of an acid and a base. So we still kind of have the double displacement going on right here. So you have, here's H and B as the ions written in the front, and they have kind of switched places. So now you have Ba, and then the H went over to join the OH, which HOH is basically the water molecule. So one thing about neutralization reactions is we're always making an ionic salt and water. And then we're reacting, of course, an acid and a base. So it's the H part in this HA that makes this an acid, and it's the OH in this compound that makes this one a base. So we're reacting an acid and a base, and we make a salt, an ionic salt and water, That is what defines something as a neutralization. And I might also call it an acid-base reaction or an acid-base neutralization reaction. But we're basically producing a salt and water, and salt meaning some sort of ionic compound. So any ionic compound is basically a salt. It doesn't have to be table salt. So table salt is NaCl, but if we made LiCl or LiF or LiBr, or we could even do magnesium chloride or calcium fluoride, all of these are ionic compounds, so they can all be called salts. Anytime we're making a salt and water from an acid and a base, we have an acid-base neutralization reaction. So just to kind of summarize what we talked about, and these are things we talked about today and last week, there's 4 different ways to tell if a chemical reaction occurred. So a gas or a solid was produced. So basically if you have, aqueous thing plus aqueous thing, and over here you made aqueous plus a gas or aqueous plus a solid, and that's telling you you're making a chemical reaction. Anytime you make a gas or a solid, a permanent color change, and this is something you'll also often see anytime you do make a solid, because sometimes that solid you make has a color to it, or it's just simply not white, or it's not transparent. Energy change. So if it feels hot or feels cold, we talked about last time. That's exothermic and endothermic are the terms. So exothermic is when it gives off heat, so it feels hot to you as the observer that's part of the surroundings, and it's endothermic if it absorbs heat, so it's basically extracting heat from the surroundings, which includes your hand if you're holding the test tube. And then we also mentioned, which I had mentioned before, there's 7 diatomics. You need to memorize these. So H2 being on the left side of the table and these being on the right side, and then remember these are our halogens. But you need to remember that these 7 elements, when they exist in nature, when they're in neutral compounds in nature, they exist as diatomic molecules. So to contrast that, the noble gases, for example, like helium, neon, argon, those are the noble gases. When they exist in nature as neutral atoms or as neutral compounds, they are just monatomic, they are just single atoms. These exist as diatomic molecules, so make sure you memorize those. And then these are our reactions, and there's one more that we actually didn't talk about because there wasn't a slide for it, but that was combustion. So we're going to add this to the list. But we talked about combination, where we're making a new compound. Decomposition, we have a compound breaking up into smaller pieces. And then single replacement and double replacement we just talked about. So single replacement is just one thing, one element bumping out what was in the compound. And then double displacement, these two are kind of switching places. They're trading partners. And the neutralization was the acid-base reaction. Now, combustion, you're probably familiar with it colloquially, but what we basically mean with combustion is anything that is reacting with oxygen to produce CO2 and water. So for example, we could have CH4, which this is methane. Methane reacting with oxygen to produce CO2 and water. It could be another thing like C2H6 reacting with oxygen to make CO2 and water. Now, what this has in common with neutralization reactions is that we're making water, but what's different is here we're making CO2 and water, where with neutralizations we were making a salt. So it's important to make sure you're comfortable with identifying an ionic compound versus identifying a covalent compound. Because CO2, we have a nonmetal bonded to a nonmetal. This is a covalent compound, and it's pretty much always going to be CO2. But then if you have a metal bonded to a nonmetal, like sodium and chloride, this is ionic. But anytime you have a carbon-containing molecule like CH4, methane, ethane, propane, other examples might be like C2H5O or something, so it doesn't have to be only carbon and hydrogens. But anytime you have a molecule that's kind of like that, reacting with oxygen, it's essentially burning, it's giving off heat, it's combustion, it's what you would normally think about when you light a match or you have a fire. and we're making CO2 and H2O. That's the last type of reaction, and again, there weren't slides for it, so that's why we didn't have a special slide in here. But combustion, I'll say hydrocarbon plus O2 makes CO2 plus water. And I'm noticing here HOH, that's the same thing as water.